Okay, we've talked about how wonderful orthobases are. So now let's talk about what to do if we don't have an orthobasis. So we want to take a sequence of vectors and produce a corresponding orthobasis. So generally, assume that we're given some set v1 up to vn that is not an orthonormal set. So our goal is we will find a set of U vectors such that the span of our VK is equal to the span of our U vectors, and UK is an orthonormal basis. So, step one. Let's start with our first vector. We're going to define another vector in here just to simplify the bookkeeping. We're going to say that W1 is equal to V1 and then normalize it. So U1 is the first vector of our orthonormal set, and it's equal to W1 over the norm of W1. So that's whatever our induced norm is, that's what we're going to use. So one thing to note is we're off to a really good start in that U1 is an orthobasis. For the span of, well, vector V1. It's collinear with V1, so that makes sense. All right. We are 1/n of the way there. Let's do the next one. Using V2, we will define W2 is equal to V2 minus the projection of V2 onto U1, and then U2 is equal to W2 over the norm of W2, but we still haven't found what we're looking for. So, but we're getting closer. U2, U1, we know that this is, well, we assume it's orthonormal and orthogonal to U1. But let's try it out. That's just equal to 1 over W2. The norm of W2 is going to get increasingly hard to write. Oops, that should be a U1. That right there is just a constant. Now it's already been determined. So there we go. We substituted in that for that, expanded it out, and we know that that's equal to 1. So we have v2 projected v2 comma u1 minus v2 comma u1. So that is equal to 0. So sure enough, we now have two orthogonal vectors, and they're both defined to have unit norms. That's why we normalized by this u. And now you can see why we introduced that, because if we were to carry through the whole thing, writing this big expression in the numerator and denominator, it would get kind of ugly. Okay, so now let's go with induction. At the beginning of the kth step, we have u1 through uk minus 1 that we've already defined. So if we're at the third step, we've already defined u1 and u2, which is actually what we've done. So we have an orthobasis for the span v1 to vk minus 1. Now I will add what happens if we have something that is not like two vk's that are say linearly dependent. We'll end up getting wk is equal to 0, and we'll skip it. I'll write that down in just a moment so it's here in the notes. But for now, we'll just assume that all of our v's are linearly independent. Okay, so let's break down this just a little bit before we go on. This is the projection of vk onto subspace capital T sub k minus 1 spanned by just the vectors that we have so far. So once we've so in other words, we're finding the part of vk that is not explained by the other previous versions of previous v vectors. And as before, we then say uk is equal to wk over the norm of wk, and we just repeat until all vk's are used. And as I mentioned before, if any wk equals 0, then we just skip it. It came from a linearly dependent vk vector. Okay, let's go through one example and see how this works. It turns out that while the process is quite simple, it's often better to do this by computer because it can get oops, delete, there we go. It can get rather there we go. It can get rather messy. So we'll start with a simple example. Say our VK set is equal to 110, 101, and 100. So it's easy to check that this spans R3, and we're going to use the standard inner product. Now, since it spans R3, you might be tempted to say, aha, I know a basis for R3. 100, 010, and 001. And depending on how you did this, that's what would come out. Or, if you do it a different way, it won't. So, for example, if I started with this one, there would be my 100, and then I did that one next, and finally this one third, that would yield standard basis. So it matters the order that we do this in, because we're not going to do it in that order. Instead, we're going to do this one first, this one second, and that one third. So let's see how this shakes down. First, U1 is going to be V1 over the norm of V1, which is going to be 1 over the square root of 2 times 110. So that's our V1. That's the easy one, or U1 rather. The next one, we're going to have to go through the steps of defining our W2. W2 is going to be V2 minus V2 with V1 or U1 times U1. So that's going to be, this first part is easy. There, I wrote down V2. Now, V2 with U1, we're going to have this 1 over the square root of 2 come out there. And we transpose and multiply. And so that part's going to be easy. That's times 1. Now that's times the vector U2 or U1, which is going to be 1 over the square root of 2, 110. So what do we have here? This is going to be 101 minus 1/2 times 110. That will give us 1/2 minus 1/2 and 1. Okay, the norm of that is not 1. So what do we need to do? Well, let's find out what W2 squared is going to be 1/2 minus 1/2 1 times 1/2 minus 1/2 1 will be 1/4 plus 1/4 plus 1 is equal to 1.5. So the norm of W2 is going to be square root of 1.5. Square root of 3 over 2 is 1.5. So now U2, which is equal to W2 over the norm of W2, will be we're going to put a factor up front, but let's do this first. 1 minus 1, 2. So we multiply that by 2. So that'll give us square root of 2 over 2 square roots of 3. Okay, we're getting there. There's U1, U2. Now you can see that this is going to start getting really ugly. This is why we typically do this by computer. So W3 is going to be V3 minus, and we have to project it onto the whole space, U1 minus V3 with U2 onto U2. That will be 1, 0, 0. That's the easy part. V3 with U1 times U1 is going to be 1 over the square root of 2 times 1 over the square root of 2 times 1, 1, 0. So that's our U1. And this one's going to be 2, or square root of 2 over 2 square roots of 3 times U2, which is square root of 2 over 2 square roots of 3, 1 minus 1, 2. So we get a half. This term with all the square roots of 3 and 2 and so on and so forth comes out to be 1/6. And so it's going to be 1, 0, 0 minus 1/2, 1, 1, 0 minus 1/6, 1 minus 1, 2. And that will equal 1/3, 1/3. Whoops, with a negative in there, and I didn't give myself enough room. There we go. 1/3 minus 1/3 minus 1/3. And that's W2. And so U3 will be W3 over the norm of W3. This is starting to get ugly. I'll push through just for completeness' sake. 1/3 minus 1/3 minus 1/3 times 1/3 minus 1/3 minus 1/3 is going to be 3 times 1/9, or 1/3, 9, 1/9, 1/9. So that's equal to W3 squared. So U3 is now equal to 1/3 over 1 over the square root of 3 times 1 minus 1 minus 1, which is now equal to, let's see, multiply 1 over the square root of 3 times 1 minus 1 minus 1. And there we go with our ortho basis. And you could try this out and see that, yes, indeed, this does the trick. And we actually have an ortho basis. But the interesting thing is it starts out pointing in the same direction as the first vector there with u1. And from then, we try to point in the same direction as u2, or as v2 when we calculate u2. But in order to make it orthonormal, we have to subtract out the contribution of v1. And so we go on building this up, and it gets uglier and uglier as we include more things. But we end up with an orthonormal basis set that follows the sequence of vectors that we were originally given. And aside from just creating an orthonormal basis, this actually turns out to have far-reaching consequences in everything from matrix inversion, solving systems of equations, and adaptive filtering, and various things like that. So that's Graham Schmidt, and we'll be seeing him again. Thank you. Have a good